All right. So as Fabio was saying, we are working on some Sablefish behavior detection. Specifically, my work was focused on startle detection. So I'm Declan McIntosh. I'm from UVic. I am a PhD student in the electrical and computer engineering department. I work mostly on computer vision stuff under Dr. Alexandra Albu. So what I'm going to talk about a little bit today is coarse-defined detection using multiple methods of Sablefish Startle detection to efficiently search large underwater video datasets. So one big issue that we had, so this project was in collaboration with Ocean Networks Canada, and our goal was basically to evaluate the influence of artificial, or to help with evaluating the influence of artificial light and other objects on sablefish behavior and vocalizations, specifically by detecting when they exhibit specific behaviors, and we limited our focus just to startle events. Also on the right there, you have my favorite video from this entire project of one sablefish startling into the mouth of another. And then, so the data that we collected was from the Barkley node at ONC, from the fish acoustics experiment phase 2 that Fabio was previously talking about. So the major problems that we had in this project is we wanted two things simultaneously. First, we wanted really low-level, instance-level, individual and multi-sablefish startle events so that we could figure out whether or not sablefish were startling each other, whether they were startling on specific instruments, or if they were startling because of the light turning on or off. And also, we wanted to be able to process huge amounts of video that ONC collects at each of its nodes really, really efficiently. Because even when these nodes were baited, we don't necessarily have as many detections as we would like, just because most of the video doesn't have sablefish startle events. Oh, there's an echo. Okay. Could you let me know if that echo is still there?
Seems okay right now.
Okay, weird.
No, I still hear it. If you have your speakers on, it's probably just that we're hearing your speakers through your mic.
Yeah, I have headphones on.
Oh.
So I'm not sure where that could be coming from. I've turned off all of my audio. Are you still able to hear the echo now that all of my audio is turned off?
We are, but it's very slight.
Okay. It's not egregious enough to.
No, let's continue.
Okay. All right, so with the Sablefish startle events, we want to be able to process this huge amount of video where most of it isn't quite very useful, and we have nothing really useful in that video, so we wanted to make something that was also very, very fast. So we created a small little data set of this. We were hoping to use a fairly small amount of annotations in order to generate our machine learning models, just because we want to be able to multiply that like manual human effort as much as possible. So first we collected the video, and then we used some very basic, not machine learning at all, just some classic computer vision methods that have existed for a long time for saliency and motion. So saliency basically tries to pick out the key regions in an image that look the most statistically interesting within the, each frame. And then we were just checking for differences between frames in these regions because that would indicate that something interesting is also moving. So when we were looking specifically for startle events, this was a good filter for us to use. And then we used a very basic YOLO v3 detector to generate our tracks for all of our stable fish. So our first method that we used was our efficient method, where we were trying to process through data as quickly as humanly possible, or I guess machine possible. So we used a 3D convolutional neural network, and we processed entire 4-second clips at a time and generated just a binary, was there a startle event or not, signal for each of these 4-second clips. And the nice thing about processing things coarsely like this is we're able to do it really, really efficiently, but we're not getting that low-level annotation that we're really wanting at the end. So we used a sequential encoder for this just to make sure that we aren't throwing away all of our temporal relationships early on in the network architecture. And then the next other key contributions that this paper had towards event detection was on the right here, we can see a decomposition of a frame into 4 input channels using a discrete wavelet transform. We actually used the Legal 5.3 transform, which is commonly used for the newer JPEG 2000 standard. And the nice thing about this is convolutional neural networks that get used for image processing all the time scale really inefficiently with higher resolutions. So oftentimes you just downsample your image to 224 by 224 pixels, really low resolution, just to speed up the processing. But the nice thing about this is the networks don't scale really poorly with increased channels. So by decomposing our image to a lower resolution, but with increased channels that still maintain all of that information in the original image, we're able to speed up the network and give it an apparent higher resolution than what it's actually being given. And then what we also used were some temporal attention modules, which allow our network to focus on specific regions of the video. Because we were concerned with discrete events of Sablefish Startle detection, we really want the network to only focus on a small subset of the clip, because that's probably, there's probably not startle events happening throughout the entire clip. And so with this end-to-end model, we had really great performance. We were able to process in a single node running a single GTX 1080 Ti at 104 times real-time speed. And while having this high speed, we were able to have a recall of about 80%. So we do miss about 20% of our startle events in this first pass, but it's still enough that we are accurate enough for what we're hoping to do. And then we have our second method, which we get our fine-tuned detection. So we run this after our first method in order to make sure that we have the fine-tuned annotations that we want to have. So we developed this method based on a few handcrafted features around the Sablefish tracks, because we really wanted to know which Sablefish in the image was startling, because lots of that contextual information of the location of the startle and the relative location to other fish could give us information about how the fish is startling. And this method does require an object detector to be run on every single frame rather than processing one giant video at the same time. And then we finally use just a simple long short-term memory module to detect startlefish in these tracks. So on the left here, we can see the specific measurements that we used. These are handcrafted features specific to our detection of Sablefish startle events. So we considered the direction and the speed that the fish were going in, as well as based off of a Laplacian Gaussian kernel, in order to basically check how much the fish is deforming visually within the bounding box. So generally when fish are startling, they're changing directions and they're visually changing quite quickly. So we use that metric as well. And then we used the actual ratio between the height and width of the bounding box over time, because as well as when they're startling, they often go into the C shape in order to change directions. And so we can see fairly clearly that there is a spike down the middle of this specific track that's corresponded to the one in the bottom right, where the Sablefish went towards the instrument, startled on the instrument, and then went away from the instrument. So this method is able to detect startlefish events on an individual basis with a fairly high accuracy, I think around 85%. And then, but this method is a fair bit slower than our other method, by almost 2 orders of magnitude slower. So we're only able to run at 1.3 times real-time speed. So this method is still real-time speed, so it could be useful for processing a single node's live stream, but it's not really useful for back processing huge data sets that ONC collects, or for processing multiple nodes simultaneously. Yeah, and that's all I have for today.
Great, thank you so much. Does anyone have any questions? Feel free to jump on camera or throw them in the chat.
Hi there, Oliver Kirsadom. Thanks for a really nice presentation. I was quite intrigued by all this, all the work you guys have done with the computer vision. Very impressive. Just wondering, actually on your last slide here, the speed, is that hardware limited, or like what kind of machine were you running that on?
Yeah, so for both of these, we limited ourselves to a single node, single GPU. So the really limiting factor is the GPU for doing this image processing. So they were both running on a fairly old hardware now, but high end for the time for 1080 Ti's, NVIDIA 1080 Ti's. They're a consumer level graphics card.
Thanks. Okay, so it sounds like there could be scope there for speeding things up if say ONC made some more powerful GPUs available to your algorithm.
Absolutely. Or we could use something like Compute Canada to spin up a huge amount of GPUs on this simultaneously.
Well, flip side, it seems like anyone with a standard computer could run it if needed.
Yeah, absolutely. Especially for the first method. Anyone with like even some reasonably powerful laptops right now could achieve like similar to 100x real-time speed performance for the end-to-end model. Yeah, so the question for chat, why were we interested in detecting startle responses? I am very much a computer vision person, so I do not, I'm sure I don't have the full story for this, but my understanding is that we were interested in whether or not the lights were affecting the startle behaviors. So when the lights were initially being turned on versus or turned off, as well as the interaction with the actual objects that were placed. So whether or not the fish was startling on an object, like we can see here, it seems to be startling related to the actual the bait apparatus versus startling with other fish or against the seafloor. And so another question for chat, did you see any difference in performance between the two experiments? Yeah, so the main difference in performance was the actual speed. And then the other key thing is really the outputs are fundamentally different. So rather than being able to say this, so for our second method for the track classification, we're able to say this specific fish startled at this specific frame. Whereas for the initial method, we're only able to say somewhere in this 4-second clip, there was a startle event or there was no startle event. So that's really the two different distinctions between them. And obviously the track classification method was a fair bit more accurate. So another thing from chat, all of your examples have light on, use sonar for light off and flash the lights. So we were collecting data, we were using data that was already collected for this project. The analysis for whether or not startles were happening from the light coming on was basically their time in the clip, because the light turns on right at the beginning of recording, is my understanding. And then Devi asked, were you able to quantify how light impacted the startle events? We have not done that yet. We're still running the algorithm across things, but we have plans in the future to do that.
Thanks for the great questions, everybody.